So no, sorry for the delay. It's an honor to have the next speaker, Mathieu Lewin, from Paris, Dauphine, and CNRS. And he will talk about Gross-Pitagevsky theory of supersolids.
Thanks a lot, Miguel. So thanks a lot for the invitation. It's really a pleasure to be here. So thanks a lot for the organizers for organizing this nice conference. Also, I'm very happy to be here for Volker. So I think I've known Volker for 20 years already. Yeah. And so it's always, so I think we never work together, but it's always a pleasure to discuss with you. I remember many interactions, many discussions that were very influential for me. So I'm very happy to be here for you. And there will be many more in the future, I'm sure. But today I will speak about the Gross-Pitaevsky theory for supersolids. I will explain what supersolid is. And this is a joint work with NAM from Munich. And it has just appeared in a PMP this year. And I will start to very quickly tell you what the result is, and then I will explain the result. So I mean, maybe many things won't be that clear, but everything you ask me, I will explain afterwards, not before. So if I want to summarize the problem, so what we will do, we will actually mix some PDE problem with statistical mechanics. So we will study a PDE, but from a stat-mech point of view. And in particular, we will prove the existence of a unique phase transition for a PDE. And this PDE is supposed to describe some kind of Bose-Einstein condensate in an infinite gas. And the phase transition will be some kind of freezing phenomenon, which is interpreted as the appearance of a supersolidity. What is the PDE? It's a very simple PDE, so here it is. So it's minus Laplace, okay, for the kinetic energy, and then plus W convolved with U squared. Everything applied to U is equal to mu times U. So that's our PDE. So the unknown is this function U. Okay, so that's the unknown. And U goes from RD to C, and D will be 1 to 3. Okay? What do I have to tell you? So this W here describes the interactions between particles. Okay, so I mean, think of a W like that, a bit like Lennard-Jones or something. Right? W has to be integrable both at infinity and close to the origin. In fact, delta will be allowed, so you can have a very large peak, but only the origin, otherwise it's a nice function. It can be negative, okay? Like Lennard-Jones, have some attractive part, and then it must go to 0 fast enough, it must be in M1. And that's the interaction between the particles. I will assume it's radial, and so on and so forth. Mu is the chemical potential, and here we will work grand canonically, meaning that we will fix U and we will look for U. Okay, so mu will be fixed, and then we look for U. So mu is just some fixed parameter. So it's called the chemical potential. What's very important is that mu will be positive, right? Because we want to describe an infinite gas, and this equation will have no solution if mu is negative. And when mu is positive, it will have solutions, but they will be, I mean, they will occupy the whole space. So actually, U will end up being in L infinity. So that's somehow the new feature of this problem. We are not looking for solutions that decay at infinity. We are looking for solutions that are, I mean, typically do not decay. Okay? That's the equation we want to study. That's the convolution. And this describes some kind of mean field interaction between an infinite gas of bosons, which is fully condensed. We can discuss this later. We will in fact look at ground states. We will look at ground states meaning that they will have to minimize the energy, but the energy is infinite. So anyway, we will look at ground states. And ground states, they will be so that you will really not go to zero at infinity. In fact, if you compute the average, the mass, if you like, of U over a ball, so this is the ball of radius R and center Z, okay? Then we will prove that this is always of order mu. It's part of the D, okay? So there's an upper bound and a lower bound for all Z. Okay, so this says that there is mass everywhere, okay? And in fact, it also says that the average density of the system is of order mu. So you can think, as usual in statistical mechanics, mu is here to set the average density of the system, right? And so just the mass per unit volume. So we think, so mu will be our parameter. We will move mu and see what's going on. And then we will get something which has density essentially of order mu. So in particular, so you see that small mu means low density. And for such cases at low density, we expect fluid. And large mu in high density, where we rather expect a solid. What does fluid and solid mean for this PDE? Well, it's very easy. Well, actually, it's not that easy, but let's make it easy. So we could define fluid just by translation invariance. Maybe a little bit too much, but why not? And what's very easy here is that it's just one PDE. So if your function is translation invariant, this is just constant. So what is happening if we look at constant solutions? So this equation has very obvious, simple constant solutions. Which we will think of as the fluid state of our problem. So there is one which is u equal to 0. That's a trivial one. But this one will never be a ground state. This we will see because it doesn't satisfy this. Okay. And there is another one, which is u equal to. So you see, if u is constant, the Laplacian disappears because the Laplace of the constant is 0. And then you can make these two terms equal, whatever u is, by just making w convolve with u squared equal to mu. And when you convolve w with a constant, I mean, you get the integral of w times this constant. So you see that the constant is a square root mu over integral w. And so we will think of this solution here as, in fact, the superfluid state. A constant solution. It's in fact a Bose-Einstein condensate, completely translation invariant. And so let me mention that this solution exists because there is a W. There's no W then. So the interaction is really crucial here. Right? We will never think of the interaction as a small perturbation of the Laplacian. The interaction is the one that rules the game. Yes. Integral W will always be strictly positive. Actually, in statistical mechanics, when you have a stable potential, the integral is always positive. Otherwise, it's unstable. So it's an extremely natural condition, and it's saying that this kind of large part close to the origin must be large enough to compensate the negative part. Let me state the theorem now. Okay. It will be somewhat a little bit imprecise, but so theorem. And then I will spend the rest of the talk explaining this theorem, both the assumptions. So we will work in dimension 1, 2, 3. In fact, we have a theorem in all dimensions, but some parts are a little bit easier to state in dimensions 1, 2, 3, and that's the physical case anyway. So first, assumptions on W. Okay? W is the main thing. So I'm going to assume that W is a short range, super stable, Short range, super stable. Even I don't really need radial. Even it's fine, but I mean, you can put radial if you like. And I will assume that. So as I told you, so W, you can allow a delta part at the origin if you like, but then there has to be a positive coefficient. Otherwise, this coefficient can also be 0, so R plus contains 0, and then L1. Okay, so that's the interaction thing of something like that. And I want to emphasize that these assumptions that I will explain later on if you ask me, and only if you ask me, are extremely general and they cover all physical reasonable situations of short range potential. So now a statement. So no, that's the whole point. Statement number one, there are ground states. Okay, so for every mu positive, there exist ground states. It's not so easy because I mean, you're in the whole space, you're already in the thermodynamic limit, and I still not defined what the ground state really is, but I will do only if you ask me. For our equation star, okay, this is going to be star, the GP equation, and if you like, they can be chosen real and positive, okay, which is very natural. Ground states are usually real and positive, but in fact, there are ground states that are not real and positive sometimes, but this I will explain only if you ask me. And then in this case, then U is related. Well, maybe I just put a constant. So there will be a constant depending on mu. Okay. Maybe I write 1 over C and C. Okay, so U will be just between two constants. It will be in L infinity, but it will never be close to the axis. Right? So it's more than L infinity, right? Because 1 over U is also in L infinity. For a constant depending on U. So this is about existence of ground states, and now I have to tell you what they, how they are. And in particular, I have to tell you whether this guy is a ground state, and whether it's the ground state, maybe, for small mu. So the theorem says that there exists a unique phase transition. Okay, so this model has a unique phase transition when I vary mu. Okay, so I'm thinking of varying the density through mu. So there exists a unique, mu c. This mu c is strictly positive, but it can be infinite. If mu c is infinite, there's no phase transition. Okay? And I can tell you under which condition mu c is finite or not. So in fact, I have mu c infinite if and only if W is positive definite. Okay, so there was no condition on the Fourier transform because if W is positive definite, there's no phase transition, very natural. But that's an if and only if. Okay, so if the Fourier transform changes sign, then there is a phase transition, a unique phase transition. What does it mean that there is a phase transition? Well, I have to tell you what's happening below mu c and above mu c. Okay, so for every mu below mu c, okay, what is happening? Well, what is happening is that we are in the superfluid phase. So namely the constant solution, which is the square root mu over integral W, is a ground state. Okay? And now there is a subtlety that it might not be unique. There might be other ground states, and in fact they are. We prove this. But I can also tell you that all the ground states are essentially constant far away. It's a little bit complicated because of vortex lines and so on. And so the statement will be they look constant in almost every direction far away. That's the statement. And the almost every is because of vortex lines or vortex points in 2D. And of course, the constant I see could depend on the direction I pick. Okay, so let me write this statement. So any ground state U I need to be strictly below mu c for this part here. Satisfies that for almost every direction omega, so I pick a direction in the unit sphere, and that's almost every, we can find a theta omega, which is going to be the phase I see in that direction. And we can find some ln and rn going to infinity, so that u is really constant. So I will look at u minus the phase times square root mu over nj over w. And this will go to 0 in L infinity of the ball. Then I look, I don't know if I'm using the same notation as before. So maybe, okay, so I have to first I put the center and then the radius, if you're okay. So then I look in one direction extremely far away. So the center will be omega times ln. Okay, ln is very large. And then I look over a very large ball located very far away in that direction. And so this goes to 0. Okay, so this is saying that in almost every direction, u is constant, although the phase could depend on where I look. And in fact, yes, there was a question. No, I thought there was a question. No, no question. Okay, good. In fact, so for mu extremely small, we can prove that the constant solution is the unique real valued ground state. Okay, and this is telling you that if you have a non-constant ground state, then it must have a non-trivial phase at infinity, like vortices or vortex lines. No. The statement is it's unique among real-valued functions. Okay, and everything here is about the superfluid phase. And so next I have to tell you what is happening above mu c, which by the way only happens when the Fourier transform of W changes sign. So maybe I should remove mu c. I mean, when we are exactly at mu c, it's a little bit. So here the statement is u cannot look like a constant anywhere. So if you give me any large enough ball, then the maximum and the minimum of u will be very different wherever I place that ball. Okay? Of course, in my mind, I think of a truly periodic function. The conjecture is that u is periodic, but we don't know how to prove this. That's a very difficult problem. And so the best I can do is to say that u varies a lot everywhere. So the statement is the following. So there exists some alpha, which depends on mu, w, t, and I think that's it, and is strictly positive, such that any ground state, u, satisfies that if you compute the maximum of the modulus of u over a ball, okay, then this guy is strictly bigger by some alpha, bigger than the minimum plus alpha over the same ball. And this for all center in RD. Okay, and some R, which also depends on mu, d, w. So that's the super solid phase, where we think that u is actually a periodic function. And I mean, there are conjectures about what kind of periodic functions, but here we can't prove anything. And so in this regime, u is essentially periodic, and this is what is happening at high density when u is larger than this critical mu c. Unique phase transition for small mu superfluid, which is typically constant but could be non-constant. Okay, and then above it, a solid in the sense that u is a genuine periodic function that does vary everywhere. So that's the main theorem. And so the talk is finished essentially. Now I will only answer questions in a way about this theorem. Yes, very good. What is a ground state? Let's start with this, why not? So you asked me what is a ground state, so where is my, it's here. What is a ground state? So let's start by defining ground states. I could also explain should I give you the menu and then you choose? Or it's almost time for lunch. I can also explain the physics why this has to do with superfluidity, supersolidity. It's a very active theme at the moment in physics, experimental physics as well as theoretical physics. And but let's start. I mean, I can also explain to you the assumptions on W, although if you think of that shape, I guess you're happy. I can explain to you many things, but only if you ask questions. So let's start with ground states. Okay. So there's a natural energy in the business, which is unfortunately going to be infinite, but I can write it anyway. Okay, so the energy, you know what it is. So E of U, so it's just grad U squared. Then I have 1/2 W of x minus y modulus of U squared modulus of y squared dx dy. And then minus mu integral U of x squared dx. Okay, so that's the energy. And I'm thinking that I want to minimize this energy over all U. I'm not fixing any mass or anything, because I fix mu. Okay, of course, I can't, because if I do this, I find minus infinity. But so definition, we say that U is a ground state if whenever I perturb U locally, the energy goes up. Of course, you're going to tell me the energy is infinite, but that's okay, because if I can make sense of the difference of the energy of the new guy minus the energy of U, and if the difference is finite, then I can ask it to be positive. So U is a ground state if E of U plus H minus E of U is positive, okay, for all H, say, it's infinity compact support. Okay. So now it's the difference of two infinite quantities, but in fact it's just a way of rewriting. So you, instead of writing the differences of integrals, you write integrals of differences. So for instance, you write integral of the grad of U plus H squared minus grad U squared. Okay, and you do first the difference, then the integral. And you do a similar thing for the rest, and all these integrals will be finite. I have to first start with a space for U in a way. So maybe I put it here. So I will assume that U is in H1 uniform. And so what is H1 uniform is just H1 everywhere with an H1 norm which doesn't depend on where I look. Okay. Okay, so I put this as a condition without any bound on the H1 norm. I ask it that it's H1 locally. I know that U is H1 locally, right? Because when I do my perturbation H locally, I need that U over there is H1 of the support of H. And that must be true wherever I put H. So that's the definition of the ground state. Okay? Some people call it the local ground state. I don't like this very much because it's true that we do local perturbations, but they are arbitrarily large when they are local. Okay? Anyway. So there's a small lemma that tells you that if you expand to order 2, well, I mean, first you can expand to order 1, and you will find that U has to solve the equation. And then if you expand to order 2, you get that a certain quadratic form has to be non-negative relation. So what is it that you get? So any ground state solves our equation. That's good. And there is in addition and satisfies some second order condition. So let me write the Hessian for you. I mean, you know what the Hessian is for this kind of problems, I'm sure. You You just have to be a little bit careful that you have the real structure of habituations. It's always a nightmare because it's always Asian for the real derivation, but we have a complex wave function. Anyway, so when you expand to second order, so you get the value of h squared plus w convolved with u squared, everything times h squared. Okay, then you have, of course, minus mu integral h squared. Okay, so that's what you would have told me is derivation, but you have to be careful that there's a cross term. When I do u plus h, there is a cross term here. And so there is a plus 2. And then I have maybe I write again w of x minus y. And then I have real part of u bar of x, h of x, and real part of u bar of y, h of y, dx dy. And this quadratic form, which is well defined on the functions of compact support or anything, must be non-negative. That's the second order condition. So you see that if u is real value, if we assume that, for instance, the constant solution is real value, then you can simplify these things because then you get a quadratic form for the real part and a quadratic form for the imaginary part of h, they decouple, and you get two conditions. So you end up at the fact that minus Laplace plus w star u squared minus mu must be non-negative. This is what you get when h is pure imaginary. And then you get another condition that minus Laplace plus w star u squared minus mu plus 2, and then u of x, u of y, w of x minus y must be non-negative, where here I write the kernel of the corresponding operator. That's the two conditions you get. I mean, very classical thing. And now let's test this on the constant solution. Okay, so for u equal to the constant, which is current mu over integral w. Okay, so I got two operators, so let me call them h1 and h2. So h1 is very easy because you get minus Laplace, because the constant solution is exactly so that these two cancel each other. So minus Laplace is very positive or non-negative, and so it's definitely okay. It's more interesting when you look at the second guy, because the second guy you get minus Laplace. Right? So what is h2? So h2 is minus Laplace plus 2 u squared, which is mu over integral w, times w of x minus y. And this operator must be non-negative, but you see, this is translation invariant now. And these two. So you can write it in Fourier, and in Fourier you get the k squared plus 2 mu w hat of k divided by w hat of 0. And then you're sure you get the 2 pi's right. That must be non-negative. Right? So this is the stability condition of the constant solution. Stability of the constant solution. And you see that if w hat changes sign somewhere, then I can always make this negative by picking mu very large. And then it fails. And so that's the reason why there must be a phase transition when w is not positive definite, just because the constant solution becomes unstable. Okay, so in fact, we can define a mu prime c, which is an Arwin method, but I think it's the minimum over k of k squared w hat of k, w hat of 0 divided by 2 w hat of k minus the negative part. Okay, and then mu c will be less or equal to mu c prime. So that's the way you can prove that there must be a phase transition, right? Because the constant solution becomes unstable when mu is large. That was ground state stability, and then why there is any other question. What else do you want to know, Volker? Yes, that's the condensate. Yes, very good. So, remarks on the physics. Yes, so the question was, what is U? I guess what is the physical interpretation of U? So remarks on the physics. So maybe the way to reformulate the question is, what is a supersolid? Or maybe a different way of reformulating everything. Yeah, what is a supersolid? Anyway, so let me remind you that we say that there is a BEC in an infinite gas. It's very important that we consider an infinite gas, infinite Poisson gas, thermodynamics. So after the thermodynamic limit, now I have an infinite gas. There is my gas. It is infinite. Right? I'm not doing the thermodynamic limit. I've done it already. So I have an infinite gas. So we say that there is a BEC when the U of one symmetry is broken. Okay. And this you can usually detect by looking whether there is off-diagonal long-range order, which, I mean, these are equivalent things, okay? Because you can look at all equilibrium states, and it depends whether you look at the extreme points or not, anyway. And so, usually one can characterize this by looking whether there is off-diagonal long-range order. What does that mean? So that means that if you look at the one particle density matrix, gamma of xy of my infinite gas, okay, then this does not go to 0 when x minus y equals to infinity. Okay, so it does not go to 0. And in fact, you can prove that by looking at an extreme point, then, so this is of course a diagonal method, whether it's x or y, but it doesn't quite matter. Okay, so this will be my u of x and u of y bar. Okay, so we say that there is BEC in an infinite gas if for an appropriate state, discuss this, the one particle density matrix has some off-diagonal long-range order when x and y are very far apart. This really looks like a certain u of x, u of y, and u of x is the BEC wave function. Okay, so that's the definition of BEC. You are more used to the fact of looking at the translation invariant case, in which case u will be a constant. If gamma depends on x minus y, then u has to be constant. But in general, it doesn't have to be constant. And so supersolid is by definition when u is really not constant. I mean, okay. I have to say there are several definitions of supersolids, and that's the easiest one. They are not equivalent, by the way. Yeah. No, that depends what state you look at. Right? So you are in infinite volume. Now you have several equilibrium states. Okay, they form a convex set. Now some symmetry is broken. Okay, so there is always a state for which gamma is translation invariant. And that's the guy that you get by averaging uniformly over all states. Okay, but if you look at an extreme point, then gamma will not be translation invariant. And in that case, gamma will behave like this with u, not constant. Okay, and so that's our u. So except so this here is only valid when x and y are very far apart. Okay, so there were lots of discussions of whether whether it's possible to have a u that's not constant for which you have this property in the physics literature. In fact, for some time, physicists thought it's impossible, and now they think it's possible. And what did I want to say? It's not the usual setting where there will be full BEC. Right? So in general, no full BEC. I mean, many of you have worked on other gases at low density, but at low density, there's usually full BEC, in which case gamma will essentially be equal to U of X, U of Y bar. Okay, but here, I mean, let me remind you, in helium, there's about, how much is it, 10% BEC only. Okay, so in fact, when you write the equilibrium equations, they are extremely complicated, and they couple the behavior of gamma at infinity, which is given by U, with the behavior at the usual microscopic scale, which is extremely correlated. Okay, so it is not true that such an infinite Bose gas which has this surface transition is described by this equation. Because that's an infinite equation which is only valid if you have full BEC. Okay, so then the GP equation is an approximation, a very rough approximation. In reality, the BEC is coupled to the gas, and it's extremely complicated, and nobody knows what to say. So there's a famous paper by Gross in 1957, who was the first to suggest this equation. That's why it's called the Gross-Pytaevsky equation. By the way, Pytaevsky was later, and Pytaevsky had a delta. And Gross had a general W like me. And that's very important because if you put a delta, the theorem works, but the theorem says that there's no phase transition. So it's not so interesting. Okay, so it is interesting when the Fourier transform of W changes sign. And although Gross messed up things a little bit, he was talking about W and not W hat. But anyway, so he was the one realizing that there must be such a phase transition for this simple model, which, however, is really an approximation to the true situation. So here what we are doing is to kind of justify, so he studied star. So he has an argument like this, like the one I described, and propose that there is a transition, if you like, okay, and that this describes supersolids. So what we are doing here is to justify what Gross proposed in 57. So for many years, people tried to detect supersolidity in helium. There's a famous story that Kim and Chan claimed that they observed it in 2004. And then nobody could reproduce the experiment, and then the paper was retracted in 2012. Okay, now people don't know anymore. Maybe they think there's no super solid phase. So here there's always a super solid phase as soon as W hat changes sign, but that's because it's a simple mean field model. Okay, so mean field predicts that there's always a transition, but in reality, I mean, the true gas is very correlated. It's not so clear whether it will always have this transition. And so now there are many results for, so now there's a new excitement, but that's more for ultra dilute confined gases. Okay, so for ultra dilute gases, and it's very active. So the first observation of the supersolid phase was in 2017, and that was a 1D situation. Then in 2021, the first 2D supersolid was observed for a confined gas. And then people wanted to check that they really had, so these kind of solids really had some superfluid properties. And so vortices, so quantized vortices, were observed for the first time in November 24. So you see it's very active. And then in March, experimental, everything is experimental, yes. And in March, a few months ago, March 25, they could build the first supersolid of light. Anyway, so it's a very active subject. And you have to choose, so, oh yes, what makes them supersolid or how you tune things, how you do it physically. No. So So, okay, very good question. So I have to tell you that the experimental situation is not covered. So first, is correlated, but the question is whether the mean field model would apply to it. It does not, because they only study dipolar gases. And for dipolar gases, the W is long range. So it does not quite fit in our theorem. Okay, so they use dipolar atoms, which have a stronger attraction far away in a way, and for which they can tune the corresponding W more effectively and force it to be in a region of parameters where you have a supersolid phase. Okay, so the problem is the mu, and you have to be able to access that mu C. It's not so easy. And so for some W's, it's easier, and then so everything here is essentially for dipolar gases or for light. And they also have some proposal of trying to do experiments for short-range W's like mine. But they say that the mu C you have to reach is a little bit more complicated experimentally, and so it was not yet observed. But I think they are working on it. More questions? Yes, Constantine. And if you observe it, you just see some bumps of, yes, how does it look like? Well, U is periodic. So you see some kind of periodic density, except that it has some so periodic, so it looks very solid, but it has some superfluid properties. For instance, you can put inside some quantized vortices, right? So exactly like for superfluids. And it also reacts in a strange way to compression, or these kind of things. Okay, so it's a solid that has some superfluid properties, or it's a superfluid. I don't know how to say, but it's a little bit misleading in a way. I mean, if you type super solid on Google, you will get lots of, scientific articles, also popular articles saying it's very, very strange state of matter because it's both fluid and solid in a way. But it's just that U, okay, is essentially periodic. Yes. No, goes to zero, tends to zero. When n goes to infinity, tends to zero. No. So maybe I can make a picture for you. Okay. So, well, let me rephrase the question in a way that I can just talk about something else for 1 minute or so. Okay, so one interesting question is uniqueness. Okay, so remark uniqueness. Okay, so is it unique? That's an interesting question. So I believe if it's real valued and you are in the fluid phase, it's unique and it's constant. And this we could only prove for small mu. Okay, we can prove it, but only for small mu. I believe it's true in the whole in the whole superfluid region. And why do I have to ask that it must be a real value? Right? Because I can break another symmetry. Okay, so I can break the U of one symmetry for U. Okay, so in fact we have a theorem which says that in 1D, with some assumptions I'm not going to write down, then U is real and positive. Okay, so in 1D, the topology makes it so that you cannot break this symmetry. Okay, but we have a theorem that says that in 2D, okay, under some assumptions I'm not going to write down, then for mu very small, there exists a vortex solution. There exists a vortex of degree 1, which is a ground state. So what is the vortex of degree 1? So it's something that vanishes at one point, and then extremely far away, it behaves like e to the I theta, where theta is now is not a constant, but is just the angle in 2D, the polar angle in 2D. Okay, so it says that u of x behaves like a certain function of x times, maybe I write x1 plus I x2 over x. Okay, we are in 2D, far away. Okay, so this guy here is e to the I theta, where theta is the polar angle. So that's a vortex in 2D. So what is a vortex in 2D? It's just a function that vanishes at a point. And then if you look extremely far away, then it has a topological phase at infinity, and it's called degree 1 because I can make only one term. Okay? So in fact, you see that this guy, so the shape is a little bit like that if I, okay, so have a vortex and then far away. By the way, it's smooth, so maybe my picture is not so nice. Okay, but you see that this guy is and f goes to a constant at infinity. So maybe I can remove f if I. Okay, well, let me know. Okay. So the statement is if I pick a direction, theta, okay, so that's my direction, right? And then I look extremely far away over a very large ball, okay, there u is constant. However, if I look in some other direction, u will also be constant, but it will not have the same phase. So in 3D, so this is a 2D picture, but in 3D you can have vortex lines. Okay, so now you have something which is turning around an axis. And now you see the problem. In fact, if you go along the axis, u is not constant. You have to be far away from the axis. So in 3D, we expect that the theorem must be, it's not for almost every, it's for all but one. For all directions but one, u will be constant. Okay, and then in one direction, it must fail. But we can't prove anything in 3D. More questions? Yes, Volker. Yeah, very good. So, yes. Zero, no, because it's non-negative. Or...
I mean, the mu is an eigenvalue, so to say.
It's kind of a generalized,
generalized
eigenvalue.
And,
Yes.
Would you have? I don't know.
I mean, think of think that u is periodic. If u is periodic, you just get a Schrödinger operator with a periodic potential. The bottom of the spectrum is at nu. It's probably non-degenerate in a way. Okay. And then you get this block balance, and so they actually compute numerically the spectrum of the operator, but theoretically it's very hard to say anything more. But let me make comments about Ginzburg-Landau. It's a very good question. Where is it here? Over here. So link with Ginzburg-Landau, and then I stop, I think. So what is Ginzburg-Landau? Well, it's a theory in a completely different setting, but for us, it just means you take W equal to delta. Okay, so you take W equal to delta, and then there's an obvious scaling, and mu doesn't play any role anymore. Right? All mu's behave the same. So in fact, you can pick mu equal to 1, if you like. By scaling, they are all the same. Okay, and so I have to tell you what's known in this case. Okay, so what's known is that in 1D, there's a unique ground state. I don't write for all mu because they are all the same, which is the constant. Okay, which corresponds to not quite to our theorem. We can prove that u is real, and we believe it's the constant. And it's unique, but we can do it only for small mu. But here, it's always unique. Okay, And in 2D, it's very nice. So it's been proved that there are exactly 2 ground states up to symmetries. So exactly 2 ground states. So there is the constant solution, and there is a vortex of degree 1. And of course, this vortex, I mean, if you take bar of it, you make it turn the other way. And you can also choose the center, and you can, of course, add a phase to everybody. I mean, you know, so it's up to symmetries. But otherwise, it's exactly 2 ground states. So for some time, we tried to prove the same for small mu in our situation. Right, but that's when you try to put many vortices. So here in Ginzburg-Landau, the theorem is you can have only 1 vortex. You cannot have 2. Or you cannot have 1 vortex of degree 2. Okay. This is very famous result. So this uniqueness here was proved by Sandier in 98 and Mionescu, based on an argument of Mionescu in 96. So we actually believe that in our situation, for small mu, there are exactly 2 ground states. And the reason is the following. It's that for small mu, remember that u behaves as square mu for small mu, and you can, in height, okay, but now you can guess what the space variation will be. And so if you rewrite everything in the correct way, so in fact, you introduce a new, so you introduce u mu tilde of x, which is the square root of, okay, so you, okay. So if u is a ground state for our equation, you rescale everything with a w. You rescale everything in that manner, and you find that it's a ground state for the following new equation, minus Laplace plus w tilde star u tilde minus 1 u tilde equals 0. And w tilde is just the rescaling of w. So it's mu to the minus d over 2 w of x over square root mu divided by integral w. So what's the point? So at low density, you if you rescale everything, you actually converge to Ginzburg-Landau. Okay, so you get Ginzburg-Landau with where you see the mass of w that you can always scale out if you like. And this is the way we could prove the behavior at low mu here. So at low mu, we do a perturbation argument around the Ginzburg-Landau problem using this rescaling. That's the way we could prove this theorem for small mu. That's the link with Ginzburg-Landau. So we actually we had to reprove many things that people did for Ginzburg-Landau in order to be able to use this uniqueness. You see, because here, so in fact, we could prove that for all the Ginzburg-Landau has a unique real valued ground state, which was not known apparently, although it's not very difficult because it's an ODE. And that's the link.
Well, there are more questions. I think we're about to finish the type of talk, but if there's another questions, no. No, let's thank the speaker for
Thank
this
you.